This is video 57 in our series Electrical Circuit Analysis. The playlist for all of our videos is at the website digital-university.org. In this video, we want to pick up where we left off in the previous video, where we had discussed the decay current of an inductor. And again, here we have just a very simple circuit, and let's say that here's a battery of 10 volts and an inductor here and a resistor of 2 ohms, and it's connected. So we know then that there's going to be a current going through here of 5 amps. And then let's say that we open this switch. Like this. We know that immediately after the switch is open, say at time t is just 0 plus, that the current through the coil just at that instant is still 5 amps, and that comes from the decay current that we had calculated, this equation that we had determined in the previous video, that for all practical purposes this is still 0, each of the 0 is 1, so the current is going to still equal 10 divided by 2, or 5 amps. And in the previous video, when we determined, when we derived this equation, we said, well, what about the voltage across the coil? We know that the voltage is L di dt. So if we take the derivative of this, that should give us the voltage across the coil when the circuit is broken. And actually, it's not quite that straightforward. The voltage across the coil depends upon how the circuit is set up. So for example, for this circuit, we open the switch, there's 5 amps of current here. It's not going to stay like that, of course. The current is going to decay. But then what can happen is the current can fall off very rapidly. So if there's 5 amps of current here, and it's going to try to push that 5 amps of current throughout the entire circuit, it has to go across this gap. And obviously this air gap is going to have a lot of resistance. Say it's maybe 600,000 ohms. So if there's going to be 5 amps of current going across that gap, that would mean a voltage drop of 3 million volts. Well, can this inductor here, can that have enough induced voltage of several million volts? Can that happen? And the answer is yes, it can, because the induced voltage across the coil depends upon the rate of the change of the current. Well, as soon as we open that switch up, the current can collapse so fast, so when you multiply it by whatever inductance value the coil has, it in fact it can act as a generator source of several million volts. And in fact, that's the essentially the principle of an automotive ignition system. But for most circuits, of course, we don't want to have that hazard where if a switch is thrown, the whole thing might start throwing sparks. So what is done is to include a discharge resistor in here. So what we're going to do then is show what the circuit looks like when there is a discharge resistor, and then for that type of circuit determine, we know what the decay current is, then for when we have a discharge resistor, then determine what the voltage drop across the coil is going to be. We're going to derive an equation for that. So the situation is like this. Say we have, again, it can be just a battery. Our coil. Then we have another resistor here. So this is R1, L. This is R2. Here's the battery. Now, first question, let's say that we have a complete circuit. What is going to be the amount of current that goes through the resistor R1 and through the coil L? And the answer is just E divided by R1. And we can show that easily enough. Let's say that there's a current coming into here, call it IS. And IS is going to get split across these two resistors. Well, the amount of current going through R1, these are in parallel, so I1 will equal, using the current divider principle, the value of this resistor, R2, divided by these two added together, times IS, the current that's being split between these two resistors. Well, IS, that equals E divided by the total resistance of the circuit. Here we have two parallel resistors, so RT is equal to R1 times R2 divided by R1 plus R2. IS equals E divided by this, so IS, here's IS right here, so we're going to write in what IS is equal to. It's E times the reciprocal of this. So IS will equal E divided by RT, or times the reciprocal of this. That's R1 plus R2 divided by R1 times R2. This is IS. And you see we have cancellations here. So we have I1 equals E divided by R1. So what that means now for our circuit that when we throw the switch, when we open the switch, like this, then at time t equals 0 plus, the current going through the coil, through this resistor in the coil, is still, especially through the coil here, is still going to be E over R1 at that fraction in time. Because remember, for the coil, there's the decay current. We'll talk about that in just a second again. We talked about quite a bit in the previous video, but it has this general formula. And again, when we open the switch immediately after that, T is essentially 0, each of the 0 is 1, so the current in the coil momentarily is still E divided by R1. Now, as we discussed in the previous videos, when we had this connected and there was a growth current going through here, the induced voltage across the coil opposed that current, and it was plus minus. Now when the magnetic field is collapsing, it induces a voltage of the opposite polarity, plus minus. And again, that voltage is L di dt. Di dt, of course, is the instantaneous change in the current. So this now can drive a decay current across these two resistors, R2 and R1. Now, we said this is the general formula for the decay current that we derived in the previous video. Except in this circuit, the resistance for the decay current is going to be R2 plus R1. So here, for the current when we have this discharge resistor, the decay current equals, it's still E divided by R1, because that's the value of the current when T, just after the switch is thrown. Because E, the amount of current that goes through here is E over R1 when we have that steady state condition. So IL equals E over R1 times E to the minus total resistance is R1 plus R2. Divided by L multiplied by the time. So for this circuit, and we can just say IL, actually these are all in series, so we can just say I. But here then is going to be, and we call it the decay current, of course, because eventually it's just going to go down to zero, but that's what the current is. And of course that's the same current that goes across the coil. Well, the voltage in the coil equals L di dt. So for this circuit, where we have this resistor across here, the decay resistor, di dt is equal to the derivative of this expression. So let's do that. Di dt will equal, we'll have this, then this part of the exponent comes down along with the minus sign. So we have minus E times this, well, no times this, over R1. Then this comes down, so you have R1 plus R2 divided by L times E to the minus R1 plus R2 divided by L times T. So there's our di dt. Now the voltage drop across the coil is just this times L. So let's just write it all out. VL equals, there's a minus sign here, L times E over R1 times this, R1 plus R2 divided by L times E to the minus R1 plus R2 divided by L times T, and these L's are going to cancel out. So we have VL equals minus E, and we take the R1 into here, and we will have 1 plus R2 divided by R1 times E to the minus R1 plus R2 divided by L times T. So here then is our equation for the voltage across the coil when the magnetic field is collapsing. The switch has been open, the magnetic field is collapsing, and we're having a decay current across this circuit here now. The voltage drop across the coil has this expression. Notice there's a minus sign here, and the reason for that is, going back up to here now, that when this was connected initially and there was a growth current coming across down through the coil, then there was an induced voltage that was the opposite polarity. It was like this. Then of course this goes away. There's just a steady amount of current going through here. But then when we open the switch, now we have a voltage of the opposite polarity. And that is what this minus sign indicates. So it might look complicated, but we did want to take just a couple of minutes and derive the formula. And what we'll do is in the next several videos then, we'll have specific examples of circuits of this type. And we can calculate the delay currents and the delay voltages and compare them to each other. So come back and join us for those videos, and we'll try and continue our discussion here and see if we can work some specific problems.